it's when I have a computer, for example, I can add multiple network cards. Let's say 3, 4, 2, whatever, multiple ones, right? So I have multiple network cards, and those network cards, they will be merged in one network card, virtual one, right? So they become one network card, one configuration, one logical. So physically, it's multiple. I think like here, for example, three physical. I have 3 circuits, 3 electronic, whatever, cards plugged in my motherboard. Right? So this is my motherboard, and I have 3 of them, and they have 3 physical ports here and 3 cables going to the switch. So in the switch, I will have three connections. Right, let's say this is my switch, and they will have the first one connected here, and the second one connected here, and third one connected here. And as I said, I can have more, or 2, from 2 and more, right? So 1 plus 1 and more. So physically, I have 3 connections in this example here. I have 3 connections of physical connections. We will not be able to test the modes, etc. in it because we will work in a virtual machine. We will not have a physical switch also to configure the switch, how it's going to load balance between, etc. But the advantage of doing this is 2 advantages. Of course, the first thing is load balancing, right? So the load balancing, instead of when we have said the data segmented here, we have segments of packets, we can send them all at once through several links. Okay. So like here, for example, I can split my time on 3. So I will divide it on 3. If I have 1 hour to send something, I'm gonna do 20 minutes to do that because I'm sending like the third in each one, right? Just an example, of course. I'm not talking about 1 hour, right? But and we have fault tolerance. So fault tolerance. So if 1 break here, or even 2 break, I'll always have 1 running. If I have more, 1 break, the rest is still working, right? So if I have, for example, a server web here on this IP that it's 192, they will all have the same IP. Not they would all have the same IP. They will not have any IP anymore. They would all work under this IP, right? So the cards will not have IPs. This logical card will have an IP in their behalf. Okay, it's much more correct to the way you should see it. So for example, 10.1, and I have a web server here. So the web server will never go down because of the network card problem here. If I have one that failed or whatever technical problem, and I have always the others that they can work. I can even also choose that I will not have this load balancing, for example, or have this load balancing between 2, and I will let 1 on mode standby. Mode standby is just if the others have problem or the communication is saturated here, so this one go up. Right, so I can always let 1 on standby mode if I want. So those are options that we can configure. Of course, we have static load balancing, static configuration. Depend on the switch how we're going to configure it manually, or we're going to do a dynamic configuration to talk with those guys here on the switch. Also, we have this option. I told you those options will not be able to configure them. They will not be accessible in Hyper-V here, but in real life we have those things. If things were physical, I mean, okay. So this is the concept of it. Please, if you have any question about it, just ask a question. Otherwise, we're gonna go and quickly configure this NIC teaming. It's pretty easy to configure, very easy to do. First thing first here is my server, for example, and as you can see, I have one network card in this one. Is it? So this is the address, right? This is the address here. I have one card, one network card that of course have some configuration inside, but this configuration will go, so I need to configure it after. You see it's 24.101 and the default gateway is 100.100 with the DNS local. Okay, so you see that I have one network card here, and all I need to do to configure it is to add multiple cards here, of course. So let's add 3 more, for example. Here we go, here we go, and here we go. Okay, I'm gonna all put them in the same switch, so we'll connect them manually to the same switch, Montreal. It's kind of, I'm cabling them all to the same location. Here we go. Now I have four adapters, 1, 2, 3, 4, and they will all show up here as it. Now I have 4 of them. One is configured, already configured, but how to merge all this card in one logical configuration so they will work as a team. This is why we call it NIC teaming, network interface or network card team. So it's just here. You see, when you go to the local server, you have NIC teaming is disabled. So we'll click here, and I will have this wonderful interface. Let's make it a little bit bigger. And I can see all the disponible cards here, right? So this is the cards that I can merge together. And I have to choose which one I merge to which one. I can either select here with control multiple ones and add to team, for example, or I will go to task here and create a new team. And I will give a name to that one, say my team. Okay, and I choose which one I want to add. And here I have some options that I told you they are gray here, right? So this one is the standby one. I see that I can choose here, or I need to select because this one should work at least. So if I select all of them to put them all in my team, I can select 2 or more, right? So 2 or more here. There you go. Yeah, so you see now it's not great anymore, this one. It's the only one, the others we can play with. But this one, I can put, for example, Ethernet is on mode standby, so the others will work, but this one will never work just in case those guys are down or need help or something, so this one will be active. I will not do that. I will choose all adapters active here. They will be all active. And I will click OK. Here we go. See, you need to give it time. It doesn't mean that it's not working here. It's saying faulted connection, blah, 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 pending. So we're going to give it a time, like a few seconds, or even refresh a little bit. And you will see that they will be all green. Warning, blah, blah, blah. Something gonna explode here, but they will be all green like this and active, okay, in a few seconds. And team interface, so I can see that I have just one team. Of course, I can create several teams in one computer, so I can add, for example, other 4 adapters and create another team here and so on. So from here, I can see all the teams that I'm having. And here you go. You see all green here, all green here. Let's go to our adapters and see what happened in there. So if I go back, you see, I see my team now. I don't see the other cards anymore. All I can see is my team, one card. And here we go. So you see, if I double click on the Ethernet properties, IPv4, there's nothing. See, I'm double clicking, trying to open it, but there's nothing, and they are all unchecked. All right. So those cards are all merged in this one configuration. So this is my team, right? This is my team. If I go to properties, now I can configure some IP address to my team here, and they will all work under the same configuration. And let's put exactly the same configuration that I had before. I think I was in /24, I guess, and 172.24. 100, 100, and my DNS was 127.0.0.1 local one. Here we go. Here we go. Here we go. All right, now let's refresh, and you're gonna see one configuration here for cards, but this card is 4 physical cards. Now they are all here, and no one is configurable. I can't configure those things anymore. You see, nothing. If I double click here, you hear the sound of clicking in the mouse, but there's nothing that can open. Every configuration should be done from the team here, right? Every configuration should be done on the team, even IPv6, whatever. This acting like a normal one, right? Like a normal card. But anything that I'm gonna do here will be those guys under that thing that I will do here. Any configuration I will do here, they will all work under that configuration, that one configuration. Okay. Hope this is clear. This is very easy. If you have any question, please let me know. Otherwise, we're gonna jump to another thing. There's nothing complicated in this nick teaming, but just in case we need to know a little bit something, whatever, right? You have the explanations of the other modes here. It's nothing. It's just about the modes of the load balancing that we do in there, right? So in the document, quick review. Yeah, you mean review. You mean the configuration just kind of, right? Reconfiguration one, right? How we configure it, or you didn't understand what is it? Configuration. Okay, this is the teaming mode. You have the explanation here, right? So there's three modes here for static teaming. This is also known as a generic teaming. So if you choose this mode, you must manually configure your physical Ethernet switch. So you see, it's always related to the other switch, but they were all grayed in Hyper-V. We were not able to configure those things here. We're able to change this one standby adapter, but those are not configurable in the Hyper-V. So in this mode, this means that the switch should be configured. We need to go and configure the port in the switch manually by a specific protocol that's called 802.3AD. So this mode is based on, this is the IEEE designation for it. Switch independent, if you choose this mode, you can use any Ethernet switch and no special configuration is needed. There's no special configuration needed, and the switch is whatever is compatible with everything. And LICP is supported by the most enterprise class switches. Those are the switch layer 3 and up, right? So they can transport other protocols than MAC addresses and ARP between the 4 cards and the switch. So it's just about the other protocols, because the switches here are enterprise class 1, not the regular switches. So they can transport and load balance, but upper protocols than the layer 2 protocols of the switch. Also support link aggregation control protocol, that we call it LICP, as defined as A1AX on the IEEE, and identify links between the server and the specific switch dynamically. If you select this mode, you must enable. So it's just something that we need to enable also on the appropriate port number of the switch. It's known as a dynamic teaming, so we call it dynamic teaming. And in the load balancing also, we have 3 other options how the load balancing happens. So they can be distributed over hashes. So we send the hash to authenticate each payload, because remember, we need to authentify all the segment and put them in order. After, when we have segmentation, it's always an overhead on the reception. And this is the backward of the segmentation, even if it's better than non-segmentation, of course. And we're going to talk about it after on the delay. We have a Hyper-V port that distribute traffic across the team, the adapter, using the MAC address or port used by virtual machine. Essentially, I don't see the difference between this one and especially the static teaming here. Should have, but maybe it's adaptable with virtual machines here. But I mean, when we have a, I don't know, hypervisor something, because we are not able to do it even in our Hyper-V here. And the dynamic, this is a default mode by default. So even our configuration today was here. And this is the default mode. It automatically and equally distribute network traffic. So it equally distribute network traffic over the port of the network team, right? And we have standby adapter that I showed you the last one here, standby adapter, that we can put one adapter for fault tolerance or failover purpose, right? So in case there is a problem with the team, so that one will take over the responsibility and work till we're gonna reconfigure or troubleshoot the team, all the whole team. So this one will not be really an active member in the team. It can have that same configuration, but it will do nothing just in case the others are not working or have trouble, so it's gonna replace them, right? So this is the standby mode. You have the configuration of the NIC teaming, right? So just a few add multiple adapters, blah blah blah, and how to select them. Wait here, so I mentioned it, right? Wait, don't be in rush. It sometimes it take 1 minute, refresh, close it, open it, but it will be green after. Okay, it's not like instantly when you click everything gonna be green. Give it a time. Okay, give it time. 30 seconds, something like that. They will be all cross red here, but after they will be all active and up. And here you go. Now you go to your IP address and you just configure it as a regular card. Okay, so let's see again this configuration here. Let's create a second team here, right? So I will let the first one, I will not touch it. Let's create a second team. So first of all, just gotta focus here, right? So first of all, we need to add cards. Let's create another team of three adapters, right? So this one is the first one, and then we'll add the second one, and I will add the third one. Here we go. I have three cards here. Okay, I have 3 cards. And let's put them on the switch that we need to be, like, for example, I will connect them all to Tokyo. Just an example, right? Here you go, here you go. All right, so I'm gonna apply, and you're gonna see that my cards will be available here. Here's my cards, 5 and 6 and 7. I will click on again on Nick Teaming. And here's my other 3 cards that I can build another team. So you see that he's telling me I have my team where I already have the 4 first. Now let's create another team with these 3 cards, right? So I'm gonna all merge them under one configuration, one logical card. And same process. So I will click here in task, new team, and I will select which cards I want to do. For example, these 2 or all of them. We'll create team 2. So give a name for that. This is the configuration, whatever. We're gonna let it like this, and we will just click OK. And here we go. So you see now I'm gonna give them few seconds, few minutes, something like that. And my team 2 will be available after here, so I can configure it. Okay, I will just refresh. And here's team 2. See, now they are all merged together under one configuration. And team 2, not yet, you see, give it a time. Sometimes better close it and open it again, but trust me, it's gonna be there. Just give it a time. They will be green. Here we go. See, so it took like 30 seconds, 40 seconds, so well, good 40 seconds, something like that. Okay, now they are all green, operational. I can go and configure my team 2. So I click on team 2, and here's team 2. It doesn't have any address, and I can configure it with some address, or even I can receive a DSCP if I have a DSCP address. So it's gonna work like a physical card, like any regular configuration. So it can even have a dynamic address from a DSCP or whatever, right? So if I want to give it a static address, here is it, just an address here. All right. Now, even in the CMD, I can see them now. There we go, IP config. So see now, the only thing that I see in the CMD is my team, the team ones. I don't see the physical anymore. All I see is my team and team 2. Because the computer here, the only cards that he recognizes, he will act like 2 cards are plugged to him. All right, he will not see those physical anymore. Yeah, they are all virtualized in 1 card. Is that good, Jaskaran? Need more? One more time? Good? Clear. Okay, good. Anybody? It's clear for everybody here? Hello. We get a virtual MAC address in case of nickname.
Yes, sir, understand.
Thanks, man. Generated. What, Davinder, I didn't get it. We got a virtual MAC address in case of nicknaming the generated combined adapter. Ah, you mean the MAC address of the, yeah, of course, of course. Look, here's it. ipconfig / all. There you go. See? All he see, Davinder, here is my team and team 2. There's no anymore the others. They don't act like a physical ones anymore. You don't see them at all, right? So we have a new MAC address just for that logical interface. Now here I have 2 logical interface, but for the computer is the 2 physical interface. This is how he see them. Okay, it's kind of if you want the whatever pool storage. Remember we did pool storage, maybe? Remember pool storage when we have a physical hard drives and we merge them in one pool storage, and after we can create the volume from those things, and you see that the computer will see them as the real hard drive, but in reality there is 4 or 5 inside that volume, right? On the pool storage, but the computer doesn't recognize them as physical. Right? He sees them just as one hard drive, physical one, but in reality, the physicals are in an underlayer, but virtualized in the same space. Here it's the same thing. So for him, the only cards that they have MAC addresses, that they have whatever, here are they here, right? So see IP config, you have the IP, they have the DNS server, whatever characteristic of a real adapter. Okay, all the characteristic of real adapter, he sees just these 2. The others doesn't exist anymore for him. Okay. So yes, sir. Yes, sir. Yes, yes, sir. Got it. Thanks. Okay, good. Created virtual volumes from that. Yeah, we created virtual volumes from that pool storage. But how the computer gonna see the virtual volumes? If you remember, he gonna see them disk 0 and disk. The more volumes he gonna pop up a new disk. So it's like we plugged a disk to that computer. In reality, are just volumes created for multiple other disks, physical, real ones, from the pool storage. It's the same thing here. The more you're gonna plug cards, merge them in the team, and that card will not be shown in the computer like a physical anymore. He will just treat that logical card as a physical one. So somehow same concept, right? Of course, we can always modify our team nicknaming, right? So I can come here, for example, and well, we can see some stat here about the parent address of the MAC address of it, and I can remove from team, right? So I can kick a card from a team here. path, or I can just let it in the team and disable it. All right. So let it on the team and disable it. I can come here also and delete a team, so I will have back all my cards on freedom, right? So they will come back as free cards. Okay. If I have an extra card now, let's see. Let's add one physical extra card. Add. So you're gonna see that everything is still flexible here. All right, now I have another extra card here, and you see I can detect the Ethernet 8, and I can just merge it to the team if I want. See, so I can always expand or shrink. It's the same thing with the hard drive. So I can always expand or shrink the team here. Okay, same way we were able to add or remove hard drives from a storage pool. Here we can add or remove cards from any already team configured. So it's not, there's no fatality, I mean, in any configuration that you already did. You can always custom that configuration with more or less cards as you want. All right. So this is important here. It's completely flexible. We still able to go back to our cards regular configuration, or we can expand or shrink the number of the cards here. Okay, we can put more cards, just merge them in team, or remove any card from a team. So I just add one here, and you see that he can detect it, and I can just now click on it and click apply, and he's gonna add it. Right, see, here you go. Of course, it's gonna take some time here to get inside, right? So, but it's gonna become green, of course. Okay. So this is how nick teaming work. Again, one last time. Any question about this, or otherwise we're gonna jump to all the thing. Are we good to go forward or something? We're good? Okay, so let's talk about sites. So when you have a domain controller, guys, like me here, I don't know, I did close the machine. Of course, sites, we will not be able to see the results because we don't have the sites have a meaning more when we have a big network, right? I mean, with the different succursal in different geographical location, because the sites is more about logic, about geography, about geographical sites. We have here always when you install the Active Directory domain and services, you're gonna end up with sites and services here. And what is the sites? The sites is all matter about replication, how things gonna replicate in your organization. Of course, you have the Word document also, or PDF. I give you there sites configuration. See it? So you can go and download it in Moodle. It's also small, right? So we're going to cover this quickly and after go to the last part for today. And we're going to finish the module, by the way, today. Okay, and I will give you, before I forget, so for saving time, please start installing 4 servers and 1 client, right? Because I'm going to give you a big lab review that you're going to do after with a little assignment, another assignment. We're going to correct the assignment next Saturday before the exam together. Okay, so we're going to do the math again and review all this transmission stuff that we're going to see. New ones just current, right? You're gonna do a lab on that. It's not the lab of yesterday anymore. I'm gonna give you one big lab today, working on as a final review before the exam. Okay, cool. Okay, for all the others who don't have those computers, so please start installing so you will not waste your time. You saw the review doc. Okay, cool. That's good. You are in advanced all the others, right? You have one step forward. Good. Yeah, you're gonna need four servers and one client, because I'm gonna give you a big lab as a final review before the exam, reviewing a lot of things in there. So yeah, and I will give you an assignment. So the assignment will correct it together, especially the transmission part. We're gonna correct it together on next Saturday, right? As a final review before the exam. Because you will have one part of the transmission calcul in the exam. You will have one question about that. Okay, so the sites and directory sites. This is also quick. We're going to cover this quickly. It's a small configuration. I told you we'll not really be able to see the result here, but at least we will understand what is those things and how they work and how we configure them. But the meaning of it, if really we have different sites and geographically, right? So geographical sites, one site in Montreal here, the other one is on London, and the other one is on Tokyo. For real, I mean, we'll be able to see the results. So we have the sites are physical locations. So it's about geography here. It's physical. It's not something inside one Hyper-V. I mean, or one virtual machine computer. So it should be physical and geographical, which contain various objects. As an example, uses computers and network devices located in an office location in London can be treated as a site. So see, when we have one geographical location, it can be treated as a site, and they can be identified uniquely from similar object located in Montreal office. Okay, Montreal office is another site. We can design 4 topologies. So we have 4 topologies of these sites. We can have single domain, single site. This is what we're gonna do. Maybe we can create 2 or 3 fake sites here. But this is the most small topology and simple one, because we have one site. So geographically they are in the same location, and we have one domain in that site, right? So this is the most common setup for small or medium site business. Okay, small one, we have one building, one domain inside, and one location. It's in Montreal, and that's it. Okay. So one site and one domain. When we set up the first domain controller in the infrastructure, it's already this. When we have the first domain, we have the first site with it, right? Because that domain, it can be on the void or in parallel universe. It's somewhere physically, geographically located somewhere in the planet. So we have the first domain in some location. We have the first site with it. This is very easy to maintain. Single domain, multiple sites. So for example, we have herzing.com, and we have one in Winnipeg, one in Montreal, the other one is in New Jersey, the other one is in Moscow, and the other one, but it's in one domain, right? So the domain is the same, it's the same domain, and we have multiple sites, different geographical location, all they belong to that same site. All right. So here in this setup, the infrastructure has only one domain. So it's one domain, under one domain, everybody working in the same domain, but extended to multiple geographical location, multiple sites. It can be based on different buildings, data centers, or geographical location sites are interconnected using by physical network links, VPN or a leased line, right? So because it's a geographically wide. So either we pass through the public network using VPNs, or as we're gonna have our leased physical lines between London and Montreal, something like that. We saw those things, those 2 configurations in the module 4 of block 1. We talked about this. And the VPN, of course, we're going to come back to this thing in our next module. It's going to be based all on this VPN. We're going to configure site to site and whatever VPN. Multiple domain, single site. multiple domain and single site. So geographically it's the same location, but I can have multiple domains all working inside with the trust, for example, or trust relationship. In one physical seat, multiple domain setup. Replication between domains will depend on the logical topology. Okay, so it's all about how these physical locations or multiple domains in one site or even multiple sites, they will replicate. The DC is gonna replicate, right? Multiple domain, multiple site. In this setup, multiple domain will be placed in multiple sites. In some setup, domain will be limited to sites. And in others, domain will be extended to multiple sites. It's hybrid, right? So we can have one domain in multiple sites, and after we have one domain in one site, and etc., etc. But how things gonna work, because they are all under the same organization at the end, but who gonna replicate from who, at what speed, at what schedule, etc., etc. We have subnets in the site. So subnets are the IP address of each site, or network ID, better, not IP addresses, but network ID of each site. And the site links is the links of the topology that we want to design, okay? And how things gonna replicate. Those, we have two type of site links. We have site links and we have the bridges. And the site links and the bridges is something like this, right? So imagine that I have here Canada site, okay? And I have these three domain controllers that I will choose who can replicate from who with which priority over the other one, because we're going to use a cost, right? And the cost, the lower the cost, the higher the priority. But let's say, for example, this one going to replicate from this one, and this one going to replicate to this one, and this one going to replicate to this one, right? So we have traffic this way from 5 to 6, and we're going to have traffic from 5 to 4, and traffic from 6 to 4. Good. And here we have another site that is London. We can also have some whatever we want here as custom. For example, this one going to replicate here, and this one replicate here. And one from Canada that gonna replicate to London, and London gonna replicate. Those called the bridge server. This is bridging link. Okay, so we can replicate at the end all the Canada to all London, and we're gonna replicate to all London to all Canada. Okay, so we're gonna see how to build these links here, how to create sites, how to put servers, different servers in different sites, and how to create these bridge links here. This is the three things that we're going to configure, but we will not see any result, of course, unfortunately, because we don't have sites. Okay, let's do that. Let's do that. So yeah, so as I said, if you go to tools and you have sites and services, it's taking time to open here. Okay, here you go. Here's sites and services. How it looked like. I don't have any subnets. I have the default first site first, and you see all my machines are in the same site because this is the domain originx.com. All right. So I have a domain child here also, rx1, and I have rx2 that is also in originx.com. That's cool. So I have 4 servers here. Okay. I have 4 servers in my domain. And let's create new site. So to create new site, this is by default, right? This is the default because we don't have any topology yet. So he took the topology by default. So if we right click on the site and we're going to click new site, and I can create the site. Why the hell did he remove the default here? Well, I have a bug here for sure, because I should find the default site here at least. No site objects were found. You may still create a site, but be sure to publish now this site. Yeah, there's something wrong because at least here I should have this default site already existing here. Let's create Montreal. Oh, He's saying that now you can put computers inside, you can add subnet to that thing, and etc. etc. Here we go. So now you see that I have Montreal. I doesn't have any machine inside. And let's say, for example, PDCX1 is in Montreal, is located geographically in Montreal. So we'll go to this machine and we'll right click and we'll move it inside Montreal. Here we go. All right, now you see that my PDC is inside Montreal here. Okay. And I can create subnet for Montreal. So new subnet. And I know that Montreal is working under 172.24.100/24. And I will link this to Montreal and we'll click OK. And there is my subnet here. All right. So subnet for Montreal. I can create another site. So new site. All right. See, that this is something weird because he should already detect those things here, but it's okay. It's okay. No problem. Tokyo. For example, I will click OK. Now you see that I have a Tokyo site, and let's say DCX2 is in Tokyo. Just fake one, right? Move, and I'll put it on Tokyo. And here you go now. Under Tokyo, I have the other one. And let's say the subnet of Tokyo is something like that, 000/8 and Tokyo. All right. Okay. And yeah, we'll not be able to test it as I told you here because those subnets, the thing that it's really important on those things are the find here. So we can use it to find computers, and here he's just generating whatever he find. But imagine if I have a lot of domain, a lot of in real subnets that they are really linked, and I want to know who is the read-only domain controllers in there, or I'm searching for a specific computer in there. Here I can find, and I can see, for example, read-only computer find, and he didn't find anything we don't have in there, right? Writable domain controllers find now, and he got me all the things that I have in Origin X here. Okay, now I can open this one. I can have many informations about this. So is it global catalog? But imagine if you have a very, very big, and I can put the site location here geographically. Where is it? Managed by who, the name of the guy. And I can even configure the VPN from him directly here to get access to that computer. We're going to do this on the next module. Okay, so you see how sites are very, very useful, especially the more bigger we have the organization and the more sites we have, so we can find domain controllers quickly here. Who's in charge of each thing, of each subnet. All right, I can have another site here, for example. Let's create another one, new site. Let's create here Ryu. And I'm gonna put RX1, move inside Ryu. One more time, this is all fake, right? We're just learning how to configure stuff here in sites. And new site, and let's say this is Paris. And RX2 gonna be on Paris, move, here's Paris. See, now I have 4 different sites, and I can create for each site its own subnet, right? So I will have, for example, 40.0.0.0-24, the one that was in talk on Ryu. I can have another subnet here for Paris. That is, I don't remember, something like that. Just fakes, everything is fake here, of course. Okay, now I can create links. I can create links between those multiple sites for single domain here. Yeah, multiple sites for single domain. This is what I'm trying to mimic. Okay. We're just currently saying multiple sites for single server. It's not for single server. I have 4 servers, by the way. All right, so I have 4 DCs here. Okay. But here I'm creating multiple sites for the same domains, and they're all Origin X. Got it? I can put whatever. I can put multiple servers in the same site, right? This is the purpose of it. It's not having one here. So it's when I have more. For example, if I do this move and I can move it to Montreal, see, I'm gonna have two servers in the Montreal, right? Be careful. The purpose of this thing is having multiple, and we can after find and filter and request quickly stuff between, and all the relationship between 1.7 and another one, right? So I can have this topology here. I can add RX1 here, like the default first one. I had 4 of them in the same location here because we didn't have any configuration before. But I can put multiple servers in each side. And this is how things work when we go to the sites. We don't need really to play with these sites when we have a simple small topology. Now for the replication, is about the protocol IP. It's very rarely that we're going to do the replication over the SMTP protocol. So we're going to play with this one and new site link, you see, so I can create links between sites. And I will create a link, for example, between Montreal and Tokyo is my first link here. I will call it Montauk. So this is my first link here, Montreal, Tokyo. And I can have another link here, new site, for example, Montreal, and it goes to Paris. This is Paris. You see that I have 2 links here. I can have other links. I can link stuff, but those should be physical links or VPN links, right? I will not just come here and link stuff from my. Here I'm doing fake things, but those should be based on the real topology, right? If I have a topology, I should already have a link between all of them somehow, okay, in the real world, geographically linked. Okay, let's say now I have Rio is connected also to Tokyo. So let's say this is talk to you. Here we go, and I can have Tokyo to Paris. All right. Now I can give priority to one link over another one, how the DC is gonna replicate and synchronize, right? So if I click in, double click in anyone, we'll find here coast, see coast, and replicate every how many minutes, and they can even schedule here. For example, Montreal to Tokyo, they will replicate with the frequency more than the others, because it's 60 now, right? And I can even change the time instead of 3 hours, each 3 hours, I'm gonna say they're gonna replicate each 20 minutes, for example, here. And change in schedule, it's gonna be just on the, it's gonna be on Wednesday and Saturday, and between 6 or 8 till 6 p.m. maximum, right? So this is how those two sites gonna replicate between them, and so go on and so go on. So each link here, what please enter a value that is multiple of 15. Yeah, okay, so 13 minutes. Apply. Okay, right. I have an object here for the some site link and created, modified, whatever. I can protect it from deletion, the deletion here, so we can delete it without and protected it back. Security, who can play with it, who can read and write, who can modify these informations here or not, who can delete it, right click and delete it, etc. So it's the same like in TFS permission here. We have read, write, and full control. And the attribute that we can use after also for PowerShell and stuff. Those are objects, because this is just an object in a database. See, this is the cost here. We can change it from here, etc. So all the configuration that we can have about all the attributes of this object, because it's a database as like the Active Directory, right? It's just another kind of it. Now I can see the replication interval is 30 minutes. The cost is 60. Montreal, Paris. See here. So I can change stuff if I want, schedule. It's the same way, right? So it works exactly the same way. Now I can create bridges between these two things. For example, if I take one link to one link, I will bridge them together by creating new site link bridge now. And now I can see all the other links that I have. And I will say, okay, this Montreal, Paris will be bridged to Tokyo, Paris over Paris. Okay. And I will give it a name here. Bridge. And I will click OK. And here's my bridge one, right? So you see that I can always modify the bridge here. And same, have security, some attribute for the objects. And can put some description. And here you go. It's the sites, right? So this is the maximum that we will not be able to test in your application or whatever here because we don't have the real sites. All is fake here. You have the configuration on the PDF, but this is the bridge that we created. We had this Paris, Montreal, Paris, Tokyo, sorry, and Montreal, Tokyo, and we bridged two links between. So we had that link here, two servers, and of course, you're gonna bridge over Tokyo and Montreal between. Okay, do you have any question about this? We're good. We're good. You have all the configuration, of course, here, right? So this is how to create new site. This is how to create new sites. You give a name to that, and you can move servers inside. Create new subnet. This is how to create new subnet. Move server to sites, and create new site link. Right. Configure cost and schedule for applications. Here you go. You have all these steps, and this is the most important one. Of course, we have 4 kind of sites. Single site, single domain. We have one domain in one geographical location, one building. We can have single domain in multiple sites. So geographically, it's split between different locations, but it's one domain. And we can have multiple domain, so different domains, but in one building, right, or one geographic location. And we can have multiple domain in multiple geographical location. Of course, this is how site work, and its purpose, it's all about how things gonna replicate, which link have more priority than the other one for replication between domain controllers. So this is the first purpose of it. And the second is to find things, find objects quickly in geographical location, right? I need to find the read-only server with its IP, with its all information in London, in that place, in location. I have hundreds maybe there, so I can have all of them shown in quickly. Okay, so I can find the object of the other sites based on the subnet. I can find the objects in there. Okay, hope this is clear for everybody, right? See, it's very easy. I told you there's no result that we can test or something, but just to know how things work inside and how to configure those basic stuff in the site topology. Clear, good. Okay, so now let's go to other thing. So please, if you go and download delay and transmission in Moodle, you have another PDF called delay and transmission. And we're going to talk about the delay of the transmissions and the kind of the delay, right? So we have 4 kind of delays in the transmission. We have 4 kind of delays in the transmission. Okay, so we have transmission delay. This is one of the most important delay, right? The delay of the transmission, what it mean? It means that in each node, like here you see computer or router, or even the next one, if I have another jump or another hop here, what is the time we need to put the bits on the medium? This is the transmission delay. What is the time we need here in this node? You see, so from the router to go to the medium. So what is the time we need to put all the packets bits here? So they're gonna jump. You see, puff, 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 puff. What is the time it take to do that? Okay. We call it transmission delay. Okay, it's transmission delay. The time required to push all the bits in a packet on the transmission medium. So they are jumping now from computer and they are jumping to the highway, right? So what is the time of all that packet it take for all that packet to jump all the bits, you know, because it's frequency, it's bits 0 and 1s. What is the time it take to put all those 0 and 1s from the network card or the device here, whatever, that they're gonna jump to the medium? Okay. We call it a transmission delay. Okay. It's very simple to calculate, whatever, in milliseconds or in seconds, right? Milliseconds or seconds. So let's say we have L, that is the number of bits in the packet. For example, I have a packet of 20 megabit, like here, right? So 20 megabit packet size. And the R is the transmission rate, bit per second. This is the bandwidth. This is the speed that I'm having here, right? So what is the speed of the thing here? So let's say this link here, I have a bandwidth of R, some R, like here they said they have 5 megabit per second. So this link here is 5 megabit per second. And to calculate the delay of the transmission is nothing but to divide the size of the packet by the speed. Okay. Remember, we have the speed is the like, for example, the distance divided by the time. Now here we are looking for the time. It's something like that. It's not really like a car moving, but we are just dividing the size of what we're gonna send divided by the speed of that hop, right? And we're gonna end up with seconds or milliseconds, like here, because I took 20 times 10 power 6 and 5 times 10 power 6 to convert to seconds. Because if I let it like this, I'm gonna have 4,000 something milliseconds here, right? So just remove this 10 by 10, and we will be able to calculate 20 divided by 5. We end up with 4 seconds. So we have 4 seconds to travel all the bits on the medium here, right? So the transmission delay, 4 seconds to put all the payload in the medium. If it's the same speed here, if it's the same speed and the same size of the payload, we're gonna have 4 seconds to do that also here. We have the propagation delay, one of the second more important, right? So usually the queuing and the processing, either they're gonna tell you what is it, or either they're gonna tell you let's ignore them, right? And even sometimes the propagation is ignored in the exercises or something. But here we need velocity to do that, to calculate that. So the propagation delay is the speed that we're gonna transmit over the medium. So what is the time from a bit that is already jumped? What is the time to travel of this? Of course, it depends on the distance of the link now, right? So the longer is the cable, the more time we're gonna have. It depends also on the bandwidth of that link. Okay, so the time required for the bit to propagate, we are talking about 1 bit here, 1 bit here. What is the time that it's here, and what did time take to get here? This is propagation. Okay, remember, transmission is What is the time of all the payload bits to be loaded in the medium, from the device to the medium, to jump to the medium, okay? Now the propagation is, what is the time that one bit take to travel from here to here? And to calculate this, so the time required for the bit to propagate to the other end of its physical path for a specific medium, propagation time is usually constant. So this is why in many exercises or many whatever, they're gonna tell you we will ignore propagation, queuing, and processing. So everything is based on this transmission here. Or they will give you a distance, and if they don't give you velocity, you're gonna use just the speed of the light as a constant. So the time required for a bit to propagate to other end of its physical path for a specific medium. The propagation time is usually constant. The longer the path, the longer the delay. Of course, it's logic, right? So the more the distant cable, the cable is longer, the more we're gonna have more delay in propagation. For example, we have x distance and z propagation velocity, usually light speed, usually, just in case they're going to mention to you, let's say the velocity is blah, 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 blah. So they're going to give you how many kilometers per second. Okay. So dprop, or delay of the propagation, is nothing but very easy, right? So the distance divided by the velocity, whatever. If they give you the velocity, you're going to divide it off that velocity. If they didn't give you that, you're going to just take the speed of light. Example, we have a distance between host and the router, like here, for example, between the host and the router. They say the distance is 1,200 meters. Okay, and they said that let's consider v is the speed of light, the velocity is the speed of light. So we're going to take that distance and divide it by the speed of light, and we will end up with something like this on milliseconds. So this is all the propagation delay. It's 33 times 10 power 7 millisecond. Okay, so this is the delay of propagation. Okay, usually they said let's ignore it. Okay, processing delay, it's something that we need a lot of information to be able to calculate it, and it's different from device to another one, because it depends on a lot of factors of the performance of the machine. Okay, so time required by router to decide where to forward the packet. It's a CPU, it's a RAM, it's blah blah, and time to calculate what is the update the TTL, perform a header of checksums calculation. If we have here routing, for example, we're gonna add those protocols. What is adding, calculating the REAP metric, etc., etc., etc. Right, the OSPF or EGRP. A lot of things here can happen. So usually they're gonna tell you what is it, because we are calculating the total delay, right? Remember, and the total delay is the sum of all these delays. So if they tell you, for example, this is ignored, this is ignored, this is ignored, you're gonna take the delay is the transmission delay. That's it. Okay. So the delay is that just one. If they're gonna tell you this and this and this are ignored. If they're gonna give you processing and queuing, you need to add them at the end. That's it. Pretty easy. So we have this one that it depends on the device, and the queuing delay is the time a packet is enqueued while the link is busy sending all the packets. So imagine that this link also have other packets coming from another. Let's say I have another link here and another device, and this device also is sending here, right? So those belong to two different communication. It's not the same communication at all, right? So the queuing, the things that I'm gonna send here, they will be queued till the payload of this link will go here, right? So this one is busy, and those are queuing here, waiting for their turn for this communication to pass over the other communication. So this is what we mean by the queuing delay. So the queuing delay, the time a packet is encoded while the link is busy sending other packets from other communication. Okay, so imagine if I have another communication here over this link coming to the packet, and those guys already sent, I received them here, but now they are queued waiting for their turn to go. That is another delay also, and it depends on the quality of the service. It depends on how performant and fast this thing is. It depends on how long and heavy the communication is here or not. Right? It depends on many other factors also to calculate those things. So we usually, they give you this number, or they will tell you ignore it. Right, so the queuing is ignored usually in the exercises. So the most important is this one, and the little less more important is propagation, right? So processing and queuing, usually they are either ignored or either they will give you that. They will tell you, here you go, this is the delay of those things. What is the segmentation? So segmentation is, imagine that I'm having a packet here. Oh my God, wow, not that big. So imagine if I have a packet here of a video, right? So I'm sending this video from A to B. Okay. A segmentation is nothing but splitting it to smaller segments. All right. So to smaller segments here, those become the packets. Those become smaller packets. So dividing bigger packet to smaller packet. This is very important because if a bit error are not tolerated here, we have an option to tolerate or not the bit error, and usually it's not tolerated because we need correction. We need to be sure that we had the right data. Imagine if I will send all the video at once here. So I'm just jumping the bits and sending all of them in one payload or one packet, one big packet. And I will get an error in one bit, and the bit error is not tolerated. What's going to happen? I need to send back all the video again. Right. And if it happened, I'm going to send back again all the video, and it still do that. But if I split it in small packets that I can send, if I had a bit error here, the only thing that I will ask for is sending that segment again, just that packet, right? So this is one of the first advantage of it. Okay. It have this advantage also that the disadvantage of segmentation, yeah, is the overheat on the reception, because it depends after on the speed of the bits. We need to rebuild back the big payload or the big packet video again, right? So we need another process to mount back all the packets in the right order, one of it. So it's gonna take some overhead on the reception here. Saud said is actually faster than here. Light speed is no, it's not traveling over the time. Well, usually light speed is this, right? So they took on consideration when you say the light speed is 300,000 kilometer per second, you are taking the I don't know, I say anything. You are taking the rounding number, right? So your rounding number, but actually the real speed of light is much more than that, if you take in consideration the rest. So we can verify this. I'm not an astronaut, but in kilometer per second and something like that. Remember, this is just an example also, right? So they just make a supposition here. You will never be able to get it by default. What do we have here? Speed of light. So this is in meter per second, and we configure it. Yeah, something like that. It's just an example of the exercise, but I thought that it's a little bit more that rounding those things here. The exact, maybe we need to see exact speed of light. So I'm pretty sure that we had a little more, and people usually say three power something, but I know that there is something more than that three, so they just round it to the three 10 power 9 meter per second, something like that. Usually this is what I met before as the speed of light. Always say exact. See, approximately something like that. Light travel is constant speed of billion kilometer per hour. Well, not hour. What is the speed of light? It's not really a big problem. We're wasting time here by your space travel or something. He goes something like that. I don't remember really. Seriously, I don't remember. But I know that maybe I'm wrong, but I know that there is a little bit more than that that people usually that they just ignore, because compared to that speed is nothing to the biggest speed. It's still here, kilometer per second. Everybody's saying, yeah, how fast is the light? Okay. Same thing, milliseconds. Yeah, let's round it. Let's round it on. But it's not possible, of course, to go higher than speed of light. Okay, let's say here it's 0. There we go. Just to make pleasure to our wonderful. There we go. All right. Yeah, 3 times 8 milliseconds, something like that. Yeah, but it was good, right? So, but he's not coming from the future. The packets are not coming from the future. So I see what you mean. It's impossible to go higher than that, because if we have higher than this, this means that the physics is should be rebuilt back, and there is. It's just a human being can find it. We already find something much faster than the speed of light. It doesn't have even the speed, it's instantly. It's called the entanglement, right? So the entanglement of the particles are instantly happening wherever in the universe. So it doesn't matter what is the distance, even if it's billion of years of light, speed of light, by the way. But it happened, the entanglement happened instantly. They don't know how it works yet. Well, we don't know how it works. All the human being, there's no human that know how it works. But of course, it's just ridiculous. It doesn't have any speed. It's instantly, so there's no even speed anymore. This is the only thing that I know that can be higher than the speed of light. Me, right? But me, I'm nothing in this astronomy stuff. So maybe there is, or other concept or other thing. Yeah. So this is just one example, right? So I remember you here. These packets, they are not coming from the future. They are coming from the same era and same year. Right? Let's see 0 here and do just switch it. We're gonna have 3, maybe something. All right. So we were talking about segmentation. So when we segment the packets, we have the advantage of these error bits. So we will not resend all the payload again. We will resend just the small segments that the bit error was being detected on. Okay, this is the first advantage. And we have a disadvantage in the other hand is the overheat here, right? So the overheat in the other hand, we need to reorganize all the segments to rebuild back the video, for example. If it's big packet here of, I don't know, a movie that we're downloading or something like that. So it's a lot segmented. This is great. Also, the segmentation depends on the links. So if we have several links or several paths to go, so imagine that I have this. Yeah. Oh God, always. So imagine I have this also here, another router. So it depends on the routing protocol that I'm using. And we have another router that can be another router connected to this one and even other one here going to this one. So I have several paths. I have several paths that I can send through. The segmentation also is wonderful because remember that queuing stuff? We can just send segments here if and others in the same time here and others the same time here. So I will send several segments in several direction following several paths to get here. So I'm gonna have much more faster way to send stuff if I split them instead of sending one payload that I should take one way every time, right? So it depends on this and on the protocol of routing that we are using here. Also, they are not all smart to do this, but there is some protocols that they can calculate in their metric, like EGRP, for example. They can calculate in their metric the load and the bandwidth and whatever is in there, and they will always find what is the best, fastest way on that moment, right? So if we split it on segments, we can also use this load balancing traffic instead of one payload. We can do it here because it's 3 hops. We have one way, one path. We don't have multiple paths, right? Okay, so he said that it's the process of dividing a full message to smaller packets. This could reduce the time of the delay instead of waiting the whole message to transmit the next hop. We start sending before the full buffering, like sending big HD video. That's cool, because if we're gonna send also the wall of it, we need the buffering, right? So we are sending all of it. So we need to buffer all the bits ready in the network card before sending the frequency here. So we buffer them all in the just the upper layer, little upper layer on the physical here. But on the segment, we don't need to do that. So we do it, but just for smaller portions. So we don't need to wait all the buffering for the rest. Okay, so we are saving time also. So every time that you're gonna segment your packet, it's gonna be faster than without segmentation, and we're gonna prove it. We're gonna prove it. We're gonna do the math, and we're gonna prove it that every time when we segment something, it's gonna go faster than not segmented. So if a bit error, so this is the second advantage here. If a bit error are not tolerated, the communication, the whole message has to be transmitted, the whole video, the whole 7 gig or whatever I'm sending here, right? So imagine that wasting of time. But here, if I segment, it's just the bit of that segment where I detected the error that should be sent it back. So this is a wonderful second advantage here. While with segmentation is just the single packet containing the error. That's it. So the segment here packet, you mean the segment, right? So the smaller packet. In the other hand, we need to put sequencing at the destination and processing more data for headers are required. Yeah. What this mean? This because of smaller packet or bigger packet. So bigger packet, if I'm sending everything here, I will have the headers, all the headers of the encapsulation in one, right? But if I'm gonna segment, I'm gonna have a second problem with that. I'm gonna have a lot of headers. So somehow my real data, not the data that I'm sending, my real data will be in reality bigger, even if it's faster. And in reality, it's bigger because each one gonna have his own header here. So you see that the data is a little bit bigger, but it's just headers, right? I mean, some few words here. some bits and some bits and some bits and some bits. It's not that complicated, but it's still a disadvantage compared to the other one, to be fair, right? So to be fair in advantages and disadvantages, we have a lot of heating processing in this one on encapsulating than the rest, but we're still faster than the other, right? We have a delay of segmentation now. It's a new thing, right? What is the time we take to get all the segments ready? So what is the time to split the payload? This is another delay that we didn't talk about it on top here, right? So we have here transmission, propagation, queuing, processing when we are sending a payload, the whole payload. But if we do segmentation, we're going to have another delay called the segmentation delay. What is the time for each segment to be ready? Okay, or for example, in 1 millisecond, each segment will be 1 millisecond, and we're going to divide on I don't know 1,000 segment. So I'm going to have 1 second as a delay, right? So 1 more second as a delay for segmentation. So each segment is ready in 1 millisecond, and we'll have 1,000 segments. So I'm splitting in 1,000, and each segment is ready in 1 millisecond. So 1 millisecond time 1,000, we're going to end up with 1 second more, but we will still faster. Even with that, we will still faster. Let's prove it. Okay, you say here that we have to send from A to B. Okay, so from A to B here with the size of 8 megabits. So I have 8 megabit. This is my 8 megabit that I need to send. Okay, suppose each link is 2 megabit per second. So each link is 2 megabit per second. Let's ignore propagation, queuing, and processing. So there's no propagation, no queuing, and no processing, right? So the delay, it's equal to the delay of transmission. That's it. Okay, let's apply the formula. We know that the delay of transmission is the size divided by the speed, right? The size, there you go, transmission rate, bandwidth is R, and L is the number of bits. So the bits, the size of the packet divided by the speed or the bandwidth. And this is exactly what we have here. So we're going to have 8 divided by 2, right? So the size divided by the speed 3 times, because we're going to have a transmission delay here, and another transmission delay here, and another transmission delay here to save them, right? So 1 plus 2 plus 3, right? So we're going to have 8 divided by 2 times 3, and we will find exactly 12 seconds. Okay. So the time that it's going to take to send the packets till B, we have the first transmission delay, second transmission delay, and third transmission delay. And each one is 4 seconds. So we have 4 seconds here, plus 4 seconds here, plus 4 seconds here. So 4 times 3, it's equal 12. Okay, good. This is without segmentation. All right, this is without segmentation. Now let's suppose the message will be segmented in 500. So we're going to split this 8 divided by 500. Okay, so we have 8 divided by 500. So each packet gonna be 16,000 bits. If we divide megabit here, so we have 10 times 6 divided by this, we're gonna end up with 16,000 bit in each segment here. See, we're gonna have 500 segments or smaller packet. So we're gonna divide it here in 500 packets. And each packet will have the size of this formula that will end up with this result. So 16,000 bits, each one. Okay. Now, the delay for the segmentation is 1 millisecond for each segment. Cool. So we have here 1 millisecond to build up each segment. In reality, we're going to have 1 millisecond times 500. So we're going to have 500 milliseconds. This is 0.5 second, right? This is a half of a second. So in a half of a second, we will split everything, okay? Because in 1 millisecond, we're going to have one packet size of 16,000 bit, okay? 1 millisecond times 500, we're going to end up with a half of a second here, 500 milliseconds. So this is a half second. We're going to put it aside. We will add it after. All right. Delay each packet, it's the same. So the delay of transmission of each packet is the size divided by the speed, and the speed never changes. It's 2, right? So it's 2 megabit per second. Okay. So it's 60,000 divided by 2 times 10 power 6, because here it's mega, right? So we're going to transfer this to bits per second instead of megabit per second. So it's bits per second to end up with milliseconds here, right? So just around 2 milliseconds. Okay, so we have 8 milliseconds now for each segment, right? So the first segment will have 8 milliseconds here, and 8 milliseconds here, and 8 milliseconds here. This is just the first segment, right? So time 3, we're going to end up with 24 milliseconds for the first segment. So the first here, number 1, will travel all this in 24 milliseconds. Not yet, because we need to add the time of all of it, blah, blah, blah. But the first one will travel on 24 milliseconds. Okay. Well, here to be more correct, we can add his own delays if we want just to talk about him, right? 25, but no worry, because we're going to add all this at the end, so it will be added at the end. But if we want to talk just about this first segment packet, in reality it's 25 milliseconds, because we're going to add 1 millisecond. It's the time of his segmentation. Okay, but we don't need to do that. We are willing to calculate the whole message now segmented, what it's going to take. So the segmentation delay is 500. It's half of a second. We already calculated this. Okay, so we are doing progress. Good. We know that the first packet travel on 24, just the traveling, right? Excluding the segmentation delay of the first packet, excluding everything. So we know that he can travel in 24 milliseconds. The first one, right? The first packet, he can travel in 24 milliseconds. Cool. The delay of segmentation is 0.5. Okay, we have 24 milliseconds of time to the first packet to reach B from A, right? Passing through the first router, passing through the second router, and get to B. The first packet take 24 milliseconds and 8 milliseconds in each one, right? So 8 milliseconds and 8 milliseconds. Okay. Now let's calculate the 500 of them, all of it. Okay, what is the delay? The delay gonna be, you know what, when we receive the first packet here, after that, each 8 milliseconds we're gonna receive the next one, right? Because they're gonna all travel at the same transmission delay. So when we reset, we're gonna take 24 milliseconds to reach the first packet, and after that, each 8 millisecond, we're gonna receive another one. Okay, plus one subnet, plus one segment, plus one segment, and each 8 milliseconds, right? B will receive one. So what we're gonna do? We're gonna do 24. The first packet took 24 plus. Now, how many packets still we have? We already transmitted the first one in 24 milliseconds, right? So 8 milliseconds, the second one jump here, right? The other jump in 8 milliseconds, the other is already here, and the third one already jumped. You see, so it's kind of machine, one coming after the other one, right? We don't wait 24 milliseconds to send the second one. 8 milliseconds, 8 milliseconds, 8 milliseconds, 8 milliseconds. So he traveled, and we have the second one. Traveled, we have second one. Received in 8 milliseconds. The second is already here. The third already jumped, right? This one is already here. The second already jumped to router 2. The third already jumped to router 1, and the fourth is already sand. And so it keep going like that. It's like a machine, one after the other one. So in 8 milliseconds after, we receive one. In 8 milliseconds after, we receive the next one. In 8 milliseconds, we receive the next one. Okay. The first one, we received it in 24 milliseconds. Here is it. Plus, each 8 milliseconds, we're going to receive one. How many left when we receive the first one? How many left? 499, because we have 500 segments at all, right? So the time for all the others to come here to be received from B, it's in each millisecond time 499. Okay, plus the segment of the delay of the segmentation, the half second for segmenting everything, plus 0.5. So we will end up with 4,516 milliseconds. That is nothing but 4.5 seconds. You see, so the segmentation, even if we have a delay of segmentation and everything, we did end up with better. It's like a third. You see, when we send all the packet, we made 12 seconds to do that. With the segmentation, even if we have a delay of segmentation of 1 millisecond, we end up with the third of the time. So the segmentation is much, much faster than without segmentation. Okay, this is why I told you we're going to prove it. All right. And if you take any size with any speed, you will always end up with faster doing the segmentation than this. Okay. So we end up with the third time sending this for almost 4.5 here, almost 4.5. So segmented message at 4.5 seconds and without segmentation is 12 seconds, almost a third time faster. Okay, it's almost 3 times faster with segmentation. Did you get it, guys? Good. Yeah, of course, it's easy, right? So the only formula that you need to keep in your mind, the first one is this one, right? So it's the data divided by the speed or the bandwidth of H1. And the delay of segmentation, if you have segmentation, you need to calculate the size of each packet. It's the size, total size divided by how many small segments we have. And you calculate the speed of each segment by the same way. So you take the size of segment divided by the speed of how many megabit you have, and you're good with it. That's it. If the processing delay or queuing delay are ignored, it's good for you. If they are not ignored, they're going to tell you this is this and this is this. And you can calculate the propagation if they give you the distance, right? And the velocity. If they don't give you the velocity, you just use here 300, don't take 6, right? Or otherwise you're going to be on the future. It's just an example. All right, so take 300,000 kilometer per second. If you have the, if you don't, if they didn't mention the velocity, if they didn't mention, because of sometimes, well, you're gonna have exercises. I'm gonna give you exercises, but we will correct them on next Saturday together, right? Just right before the exam, we'll see all this again together. I will give you 2 exercises, one in the assignment and one in the lab. Okay, but sometimes you're gonna have something like this. I can tell you this is A. And this is B, right? And I will tell you here the speed is 5 megabit per second. And here it's 5 megabit per second. But here it's 10 megabit per second. And here it's 2 megabit per second. So see, it's complicated now. All right, and I'm sending a packet of payload of, I don't know, 60 megabit. Okay. So here I need to calculate how many times the delay of transmission in each one differently, because here I'm gonna put 60 divided by 5. Here it's 60 divided by 5, so it's the same. So it's 2 times 60 divided by 5, right? So it's 2 times 60 divided by 5 plus 60 divided by 10 for this portion here, plus 60 divided by 2. Okay, now this is how I'm going to calculate the delay of all the payload. Got it? So sometimes can be a little bit different than what you expect. In the example that we did here, all the speed was the same, but sometimes it's different. Okay. And what if I can add at the end here? I'm going to tell you here, we will not ignore the propagation delay. And I will give you here, for example, this is 20,000 meter per second, kilometer or something like that, kilometer distance, 2,000 or 20,000 kilometer for this third one. Right, so you need to calculate the propagation for this one here. That's going to be 1,000 divided by the velocity, whatever is velocity. Okay, so if it's mentioned something, so you're going to calculate it. Otherwise, you're going to put the 3 whatever here kilometer per second, and you're going to calculate that, and you will add it to this at the end. Okay, now I can say that no, it's not like this. This is not just a message. This is segmented on 1,000 segment. This is segmented on 1,000 segments. Sorry. Right. So I'm gonna put here 60 power 6 divided by 10 power 3, something like that, to get the size of each segment. To get the size of each segment. And I will do exactly the same after. For each segment, I need to calculate this portion here and this portion here, because it's always the speed is different now. And I will tell you I have a delay, for example, 0.2 milliseconds for each segment. So 0.2 times 1,000 here, to be able to find what is the delay of segmentation. Right? It's something like this. So in the end, this one gonna end up with 200 millisecond, the total delay of segmentation, because this time this. Right. So this is how things work. It's just math and logic. You have one main formula. It's the delay of transmission is the data divided by the speed of that range, of that hope. Right. Any question, guys? Do we have any question? We're good. Any question? If you don't have any question, I'm going to give you the assignment, explain to you what to do. Okay, thanks. All right, so let's go to the assignment. One more time, one of the biggest of the cons of the segmentation is the overheat on the reception, right? Because we need to reorganize all the segments to organize the real payload here, and also the data going to be whatever bigger, because we're going to have a lot of headers in there. Okay, each own small segment, he will have its header, but we're not talking about the cloud data. Header is a header. It's just multiple of 32-bit, something like that. It depends on the size and the information that you have in there. Okay, let's go for the work, and we're gonna meet on next Saturday. I'm gonna give you the correction of the this whatever assignment. And where is the assignment? This is the lab, and this is delay review, I guess. Yeah. Okay, here you have some subnetting. Okay. Try, assign, mask, blah blah blah. So it's just a little review about subnetting, and you have some conversion here. How many bits in 15 megabit? How many bit in 15 megabytes? Sorry, here. And this is megabit. Convert 1,600 kilometer to meter. Convert 32,000. Sorry. Milliseconds to a second. And what is the NIC teaming? Give two advantages, blah, blah, blah. Some questions about stub zones and DNS. And this is also review questions about DHCP and sites here a little bit. Another exercise for the DNS, you know, the recursive and iterative requests. And I already gave you the correction for the last one, right? Because you did it and you didn't know if you were correct or not. And I already gave you that one. Where is it? If you go to DNS on top, you will find correction of assignment. So you'll be able to follow now the right one. Here is it, DNS assignment correction. Okay, so I give you all the correction in there. And here's the table that you did, right? Here's the table that you did in there. So following all the requests of the iterative, which one and which one. So you're gonna do exactly the same exercise with different logic in there for this one, right? So you add how many you want here. Depend how many you need. If you need to add, of course. If you can do everything in one line, do it in one line. All right, all right. It's not limited here, right? So you add more. You have a scenario here for from a computer that is requesting a server, a web server on the final address. Then he need to pass over many requests to resolve the name of this www.jupyter.com. He's looking for requesting the page index on that server. So write all the steps. And here you have a good, wonderful, big scenario of the delay. So it's consider a message that have 20 times 10 power 6 bits. Okay, so we have 20 megabit per second, megabit, not per second, sorry. So this is just the size, long. So the payload is 20 megabit. That is to be sent from source to a destination, which are separated by 3 routers in between. We have 3 routers in between. And he said that suppose each of the 4 links, we're going to end up with 4 links because we have 3 routers in between. Each 4 links have 5 megabit per second. So we are sending here, and we have 3 routers in between. And here we go. Now we end up with 4 links, and each link, he said that it's 5 megabit per second. Okay, each one, all of them equal. Okay. Ignore propagation, queuing, and processing for now, right? And consider sending the message without message segmentation. So we don't have segmentation when we have 20 mega. How long does it take to move the message from here to here? This is pretty easy, the first one, right? So you need just to do 4 times 20 divided by 5. Okay, so this is the first formula here for A. How long does it take? Keeping in mind that each router use store and forward packet switching. So there's no delay here. So it's just a store and forward, store and forward, store and forward. Packet switching. What is the total time to move the message from source and destination? There we go. So the total time is this one here. Question B, now suppose that the packet is segmented, but from router 1. Be careful here, right? So another trick we can add in questions. So he said that the segmentation didn't happen here, right? So here we send the message, the wall message, but router 1 start doing the segmentation. Think about it. It's a trap. Into 800, so we have 800 segments here. 800 packets. What is the size of each packet? You take 20 meg divided by 800, right? So 20 times 10 power 6. You're going to find how many bits in each segment packet. What is the size of each packet? How long does it take to move the first packet to the second router? So I'm looking the first packet, the first segment here. How long it's going to take to move it to the second router? It's pretty easy because of this. Whatever we're going to find it, we're going to divide it by 5, right? Because remember, this is 5 megabit per second speed. Okay, so all this divided by 5, we're going to find the time for it. Packet to the second router. What is the total to move the message to destination host? Think about it now. It's pretty interesting because we're going to have the whole message send here first. So we're going to wait till it's going to be. So we're going to whatever have delay here, for example, 4 seconds or 5 seconds or something that we're going to find here, plus the same thing we did in our example, but now from router 1 too. So we need to add the whole time that the message was being sent here. All right. So we didn't segment it here till we received the whole message first. So the whole message was being sent. Okay. And after here, we started segmenting. So whatever the time we're gonna find here, so you see this time we're gonna find here, we're gonna do that time. Let's name it T. So I will let all the math for you. So let's name it T. So T times 3, because 1, 2, 3, we're gonna find the whole time for the first segment to travel from here to here, right? And after, let's say T, so each T, we're gonna find we're gonna receive the next one. Each T, we're gonna receive the next one. Okay. So we will still have 799 times that T plus T times 3 for the first segment to travel here, right? Plus the whole payload traveling from A to B. But it's, for example, 4, right? So I'm going to say 4, right? So this, plus this, we're going to find the whole packet from A to B. Right? So what is the total message to move the destination host? Compare this result with the first. So we're going to compare it with this one. Of course, we're going to find that it's smaller, much smaller. Usually it's the third, something like that, right? But we're going to find that it's smaller than this, so it's faster doing the segmentation here. What are the reasons to use segmentation? Well, we said what is the advantages. We have 3, 2, or 3. Discuss the drawback. We have 2 of them. Remember the headers and the overhead on the reception. And here, let's consider the velocity. Do you see here, Saud? The velocity is not the speed of light anymore. This is not time traveling again. It's 2.5. So he gives you the velocity and he gives you some distance. So let's consider the velocity and distance from each hop. Oh, be careful, from each one. Right. So it's time 4. Whatever you're gonna do here, your formula, it's time 4. 1, 2, 3, 4. So from each one is a 16,000 kilometer divided by the velocity. You're gonna find the delay in 1. Time 4, you will find the propagation delay for all of it. Now, to find the thing is this plus what you're gonna find on the propagation delay. You will find the real final delay for the last question. Well, I tried to guide you, and I give you almost all the answers, but we're gonna correct this together, of course, next Saturday, right? This one and also the other exercise that is interesting in the lab So please get this assignment ready for next Saturday morning before the correction. Okay. So start doing the lab. Forget this one for now. You have all the week after just to work in your paper here because it's all theory, right? It's all theory. So you have 1 week. You can work on 1 week. On Saturday before starting the correction, you're going to submit this. Now focus on this lab because this is what you have to submit today at the end of the day. See, it's 10:30. You have all the day to do that. Here is the lab. You already started installing the machines. I told you this morning at 9, right? So your machines should be almost installed. You have here 3 segments: Montreal, Tokyo, router X1, router X2, and you have London. And you have the first subnet. So this is the third subnet of this. So this is the first subnet. This is the second subnet. It's the second subnet of this. And the fifth subnet of this become the third block here, right? You have one server, routingx.com, second DC, it's here, and this is the first DC. So they are in the same domain. So this is a second domain controller in the domain routingx.com. You have one domain. You have DHCP here, you have DHCP here, and you have one client in Tokyo. Okay, you have one client connected to the switch of Tokyo between these 2 routers. All right. Well, first of all, everything should ping. So you need to configure your static routing. Be careful. The IP address that you're going to give on this subnet to the server, it's a NIC teaming, right? So 1, 2, 3, 4. You have 4 connections here going to this switch. So you need to configure your first here before starting doing the domain or whatever. You need to start with the NIC teaming here and put the address, whatever you're going to do, you're going to give from this subnet. Okay. And you have some questions here. PDC X DHCP serve Tokyo. So Tokyo is taking its DHCP from PDC. Okay, Tokyo, whatever is here, is taken from here. The client Windows X1 with dynamic where he can join the domain. So the client, he can join the domain over Tokyo with the configuration that he saved from a DHCP of the server here. Cool. Second DC is a failover DHCP for Tokyo. So this one is a failover for this zone. See, Tokyo is created here, and we have a failover of that zone in this one. DNS PDCX contain 2 extra primary zones than the Active Directory one, because we have the zone of the Active Directory, and he said we have 2 extra other zones. One is MontrealX.com with inside a fake computer that is Omega X. This is the IPv6 of that computer and the IPv4 of that computer. And we have a reverse lookup zone, for the range of the client of Tokyo. So we need to know what is the IP here, network ID, and we need to create a reverse lookup zone for the Tokyo here. Cool. DNS of second DC contain a step zone for Montreal X. Okay, so Montreal X we created here. We have a step zone in this DNS for Montreal. A primary zone named LondonX.com. Okay, so here we have another zone named LondonX.com with the computer, a fake one, right? So we have another named Delta X, IPv6, some IPv6 and IPv4. And create conditional forwarding in PDCX for London. So London is here, and this guy is pointed to this DNS, and with the help of the conditional forwarding, he will be able to NS lookup London, right? So when he asks this conditional forwarding to go to London and give him the answer back. So we'll be able to NS lookup this computer over the conditional forwarding. Okay. PDCX have NIC teaming of 4 network cards. You already did that. PDCX site in services contain 2 sites, London and Montreal. So here you go to sites and you create London site and you create Montreal site. Their subnets is configured. So you already have the addresses. Here's London and here's Montreal. So you configure their subnets here. The subnets, their subnets is configured and their server are assigned. So you go to the Montreal site, you assign PDCX there, and you go to London site and you assign second DCX in the London site. Okay. They have link with the cost of 60. Okay, so they have a link in between. So Montreal and London have a link of cost of 60. Good. If you move Windows X1 from Tokyo to London side switch, okay, so we're going to disconnect this guy from here and plug it to the switch of London. Site we switch, he will take a TCP IP automatically coming from a DHCP here. So he will take another configuration coming from this DHCP here. Remember, to be able to take this DHCP over Tokyo, you need a DHCP relay agent here, right? And in the second one, we don't need DHCP relay agent because of when we move him to London, him and the DHCP, they are in the same segment. So we don't need a DHCP relay agent here. It's not anymore this DHCP. When we move him, it's now this DHCP who is taking in charge everything. Automatically from second DHCP, and also he will be able to join the domain. Okay, so he's taking a configuration here and he will be able to join the domain from here. Think about it. Yeah, and after we have some delay here. So let's send a message of 36 megabit from PDCX. So we have 30 mega that we're going to send from here to here, right? So from PDCX to second DCX here. So, and let's say Montreal and Tokyo operate at 4 megabits. So Montreal and Tokyo here, their speed is 4 megabit per second. But London is 5. London is different, is 5. What is the delay if the message is not segmented? So we are not using segmentation. What's going to be the delay of the whole message sending from this server to this server? Okay, ignoring, of course, ignoring the processing delay and queuing, since I didn't talk about them here, so you just ignore them. Now the message is segmented from PDCX, so the segmentation star here, right? And it's segmented on 900 packets, smaller packets, in 0.5 millisecond for each one. So if you want to know all the segmentation delay, you need to 0.5 times 900, you will have the all delay of segmentation. If you want to know the size of each packet, you need to take 36 megabit divided by 900. So you will find the size of small packet. What is the total delay for the message? Now, when it's segmented, what is the total delay to send all the segments from here to here? Of course, compare the two results. Of course, next Saturday, we will correct this together also, this part here. All right. Please, 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 please. This is something that you need to submit today till 4 p.m. you have. All right. Joban, nobody leaves the classroom before he submit. He submit the work he did, right? If you didn't finish, you submit what you did. That's it. You should finish. There's nothing complicated here. If you know how to do it, you know. If you don't know, you don't know, right? So all you need, it's gonna take you maybe 1 hour or 2 to configure all the IP addresses. Let's say, come on, you're gonna do it very, very, very slowly. 20 minutes to calculate all the subnets here. 20 minutes, it's a lot, right? You can do it in 5 minutes. Let's say 20 minutes here. Let's say you have 1 hour to configure all the IPs, and another 1 hour to configure the static route and the DHCP relay agent and the DHCP scopes, right? You still have all the rest of the day to do the sites and the whatever here, right? The A records inside the DNS and the stub zone and the condition. You still have like 3 other hours to configure those things here. So you have time. Don't tell me we don't have time. It's 10:30. Imagine. So you have all the rest of the day till 4 p.m. So you need to submit this lab today. Okay. Once you do that, you take all the rest of the week to do your assignment. Next Saturday, when we're gonna meet, you're gonna submit this assignment, and I will give you the correction of the assignment. And of course, we will correct the delays. The delays, this one and this exercise also of the lab, we're gonna correct them together. Okay, We're going to correct them together just as a review before the exam. Remember, the exam is next Sunday. You're going to have 3 quizzes in the morning and the lab for the rest of the day. It will be on campus one more time. You are not allowed to pass your exam online, right? Just in case, Tina going to send me a list of students telling me, hey, Hamza, those guys, we allow them to do that, right? So if I don't receive that list, or Tina will not allow anybody to do it online, you will not be able to pass your exam online. So you will be on the classroom. All I'm going to do is to give the passwords of the quizzes to Joman. That's it. And the PDF. Once you finish the quizzes, they're going to give you the PDF and you will work on your exam in the classroom. Nothing more. Okay, so one more time, if you have any excuse or any whatever, it's private, it's your life, I don't get in there, right? Please contact Tina, right? So if you see that you will not be able to make it, one more time, it's your life. I'm not a policeman. I don't care about whatever. I told you, even Christians said it in the message. It's better for everyone to stay online, of course. But I told you it's a matter of work permit for the international students. So they need to have that whatever percentage in the classroom from the 31 January. I know it's headache and shitty, but we need to deal with it. We don't have a choice, right? Do we have a class on 19 February? 19 February, we should maybe? I don't know what is happening in 19 February. Okay, could you tell me what is in there? What is 19 February? I don't know about the holidays or whatever in my mind. I never memorize those things. But the 1st of January is the only one that I memorize usually. So I know that. Okay, TBG, TBB. Saturday, February 19. Yeah, we're gonna start TBN on that day. Here is your schedule. Right, I already put your schedule in Moodle that you can see it when you go to your class C22. You can see all the day off coming, right? But I don't know why you asked about 19 if we have class or not. What is in 19? Is there something in there? Because maybe it's wrong, right? So I need to check. Davinder, what is in there on the 19th? Is it something? Just asking. Okay, I thought maybe Jesus died or something like that. You know, there's a lot of these things. It may be his holiday. So it's your reincarnation, Davinder reincarnation, not Jesus one, right? No, seriously, I don't know about the holidays. I never memorized those days. I love them, by the way, but I never memorized them. So, but you see here in the schedule, you don't have any off. The next off gonna be the 16 and 17 April, Easter. Okay. So tell April, I'm sorry to tell you that, but March till April here, 16 and 17 will be off. So this is the next off. And after that, this is the next off here. May 21, 22 is the Victoria Day weekend, right? But this is all your schedule. You can see it in Moodle. You can see it, right? You can see it. You have access here. You have access here, guys, right? When you click in your class, you will be able to see this table. Please, anybody can confirm that you all guys can see this one, right?
Yes,
Hello?
sir.
Okay, cool. All right. So here you have all the off day. Maybe they did mistake because this is the schedule they gave me, right? I don't do schedules. This is the schedule that they give me. I don't know if there's something here they didn't mention or they forget about it. You know, they are human being. They are not DSCP, so they can do mistakes or forget things. But till now, this is the off days coming. Next one gonna be on 16, 17 of April, but the 19th, we're gonna start a new course. This is TBN web server. We're gonna talk about the HTTP request. We're gonna talk about the details on FTP request, active mode and passive mode of FTP. We're gonna study all the kind of VPN that we can do in Windows, site to site and remote access ones. We're gonna talk again about the encryptions. Remember the stuff and algorithm and Diffie-Hellman and whatever, private key, and so all the security related to the VPN, IPsec, and so this is coming here. And we're going to configure web servers again, right? But in the domain controller also, and we will have also the IP forwarding here. We will build like kind of proxy server, something like that. We will trick the client asking something in one computer, but that computer he will go and ask in the real one. So we will hide the identity of the real one. We will do it, right? So port forwarding here, we're going to do the port forwarding. So this is what is coming on TBN. It's an interesting class. It's an interesting course with all the headache of the VPN happening in there, because sometimes the site-to-site glitch, but it's okay. We will get through it, right? And we will also configure at the end, I guess, if I remember the CMAC here, something that a file, when you execute that file, it will automatically configure the machine of the client with the specific VPN so he can have access. We have a very interesting lab coming here on the web server class. We have a lot of theory also about all the VPN and the HTTP and stuff, right? There is it. Exam is on the 30th February, see, of TBB. We are doing TBB here. 30, right here. You're going to have 3 quizzes in the morning. One more time, 3 quizzes. And the lab. The lab, it's all that we covered. Focus on this lab here, right? So if you're going to understand what you are doing in this lab, your exam will be pretty easy. Okay, your exam will be pretty easy. So focus on those things here, please. There you go. Okay, guys, any question, anything? Or I'm gonna let you practice. Take a little break, right? Take 30 minutes. We skipped the break today. Sorry about that. So you start taking a little break of 30 minutes, and after you come back and start working in your lab first, right? Because this is what you need to submit today. And you let the assignment till next Saturday. We'll have the whole week to work on it. Any question, anything before we leave? Are we good? Are we good, guys? So please confirm that you're good, right? Sure. Okay, guys. So see you on next Saturday. If you need